Hey everybody, welcome back to Bayesian. So we're talking about multi-level models. This is the second lecture on multi-level models. And if you're wondering what all the hoopla is about, please do look back to last lecture where we discuss multi-level models in general, we motivate why we care about them, and we compare multi-level models to using, for example, a categorical variable to represent stratum. So we've been dealing with a data set where 18 volunteers were asked to be sleepless. 18 volunteers went 10 consecutive days on 3 hours of sleep, but they were on regular sleep on day 0. We fit one model. The model we fit thus far allowed for different random intercepts. And so they allowed every person to have a different starting point. The intercept being, of course, their reaction time. And this is observed data on the right here. So the intercept being their reaction time at day 0, which is just their natural ability. We're allowing each person to have their own starting point, which is essentially allowing each person to have their sort of natural reaction time, their natural ability. Now, on average, we show that when we average over all of our subjects, we get the subjects got about 10.5 milliseconds slower per day. And however, there was a pretty sizable between subject standard deviation of 39 milliseconds, which resulted in a fairly large intra-class correlation. And if you don't know what I'm talking about, again, please do look back on the previous lecture. Now, just to make sure, we can put out, using this command here, we can output the intercepts per subject. And these are, alpha plus U1, alpha plus U2, all the way down to alpha plus U18. Why 18? Because we have 18 subjects. So each one gets its own random intercept. We get a credible interval per intercept because we're Bayesians, right? We just get the posterior distribution. We pick off the 2.5, 97.5 percentile. We get a credible interval. But this slope is identical, and it's just driving the whole point home that we only allowed subjects to have their own intercepts. We forced all the subjects to react to being sleep deprived equally. So the fitted lines, and there's one per subject, so 18 fitted lines, reflect all of this as well. They're all parallel lines, right? They all have the identical slope. And they do, however, have their own intercepts. And so this between subject standard deviation basically says, well, you apply the normal rule of thumb. You say 68% of my subjects are going to be within 1 standard deviation, right? And 95% are going to be within 2 standard deviations. So you're saying with these estimates, I'm going to round that up to 40. You're saying 95% of the population is going to be within 40 milliseconds of 251. So that gives us a sense for the uncertainty in the population, as well as an ability to fit the data for each subject. Here on the right, I just break it out, where I have a separate panel per subject. And you can see that we fit some subjects really well. This one, maybe even this one, and some subjects not too well, for example, this one. So there will be a need very quickly to allow not only the intercept, but also the slope with respect to days to vary by subject. And that is what we called random slopes last time. I can perform the posterior predictive check, and I have it by subject here on the right. I have it overall here on the left. Both are useful. We see that we really are hitting the mean for every subject. This is very good. I'm very happy with this. This is a bit off, so maybe a little poor fit. The overall mean, is here. It doesn't quite capture the peak of our observed data, but it's not terrible either, given that there's only, one slope in here and a few intercepts. So the next big step for us is to be more general. And in addition to the random intercept, allowing every subject to have their own intercept, also let every subject have their own slope. So conceptually speaking, or even scientifically speaking, in terms of sleep science, lack of sleep will affect subjects in different ways. Allowing this W term to modify the population slope will allow us to account for the unique characteristics of each subject. Maybe genetically, they're just really good at dealing with no sleep. Maybe they've received training. Remember, these are volunteers. These are volunteers. Maybe they received training about how to deal with lack of sleep. Maybe some of these folks are single parents, and so they can't deal with lack of sleep because they already have stressful lives. So notice that with this addition, we now have subject-specific intercepts, as in the previous model, and subject-specific slopes. Now, you guys would have seen the top pair where we first generate a between subject intercept, and that goes to inform how much variability there is, how much of that deviation we observe away from the population intercept. Notice something, if we look at a sort of a corner scenario, if that sigma is about 0, then all of the UJs are going to be about 0. And so, you imagine one subject being, 1% slower than the population intercept, one subject being 1% faster. If that standard deviation is low enough, then it will be sufficient to just include the population intercept without needing to account for the different subjects. Though if this sigma u is large, then these deviations are going to perturb, they're going to modify that population intercept in different ways, to bounce it up and down. And so the larger that sigma u, the more necessary it will be for us to include it. And of course, if you look back at the equation for the interclass correlation, right there, this is sigma u squared, right? The larger the sigma u, holding all else constant, the larger the interclass correlation, the greater the need to account for this clustering due to stratum, clustering due to subject in this case. Okay? Okay. I feel like I'm reviewing, but that's okay because there's a lot of information sort of happening at the same time. So let's focus on the new material. The new material is happening right down here, and it looks exactly like the old material. We're taking our little deviations around the population slope. Sigma W is a different parameter. It's going to get a half normal distribution. And I'm about to flip to R to do a prior predictive simulation. But you will notice that we often have to set the between slope variance to be lower than the between intercept variance. And that sort of makes sense. Intercepts capture sort of initial conditions, and slopes capture associations. And it's very rare that the difference between associations, the difference in growth, for example, are as large or larger than the difference in initial conditions. So more often than not, there would be less variability in the slope than in the intercept. If not only because of the units, right? The slope isn't, is a rise over run. The intercept are the same units as your outcome variable. So there's a lot of reasons why that second sigma is going to be less. It's going to be a smaller number, and I will demonstrate to you right now what I am talking about. So prior predictive simulation last time was pretty complex, so I'll just go through it this time, kind of pointing out all the different ways, all the ways in which this is different than the single level prior predictive simulations we've been running in the past. A reminder of what our mean is. This is, to be clear, mu ij, ith day, jth subject. We're going to draw our 500 different realizations from a half normal distribution. This library is needed for the half normal distribution. And this first line is exactly as we saw last time. When I draw this, here is the prior. All right, so it looks like the half normal is fairly flat near zero. That's why we like it. It doesn't have weird spikes, doesn't explode to infinity near zero like the exponential does. And then it decays for larger values. The mean is going to be slightly smaller. The mean of this prior distribution is going to be about 80% of 50. About 80% of 50. We are introducing the random slopes, so we need the between slope standard deviation, and it's going to be drawn from a half normal 20. Here, I'm just setting up a receptacle, an empty receptacle for my random slopes and random intercepts, those deviations from the population intercept, deviations from the population slope. And now I conditional on each individual draw of that sigma u, I will generate a set of 6 random intercepts. Conditional on each random draw of that sigma w, I will generate a set of 6 random slopes. Why 6? I don't want to have 18 panels. It's very hard to see even with 6 panels, but I'm going to have a separate panel per subject, and I will have 500 different a priori regression lines within each panel. So draw my sigma u's, draw my sigma w's, make a receptacle, and now generate my intercepts from a normal distribution, mean 0. This is what's happening. Oops, sorry about that. Right now, we're on this spot right here. So I will generate 6 different intercepts from a normal distribution, mean 0, with conditional on each sigma u, and then a different normal distribution for the random slopes. Right over here, right over there. Okay. Here is my population intercept. I center it at 250. Why do I center it at 250? If I go back to my observed data and I look at their performance on day 0, the mean was definitely around 250. And the standard deviation of 50 is very reasonable. The slope, same thing. Look back at my data. A slope of a rise over run of 10 is very reasonable. Hyperstandard deviation of 10 is reasonable because I'm still allowing for the possibility that lack of sleep doesn't affect my subjects at all. They're all, fighter pilots. But it's not so big that it's still far more likely to be positive than negative, right? And that's kind of what I'm seeing with this red line. And with just logic, the longer you're going to be without sleep, the more it will affect this, and we will become slower. Our reaction time will become longer, less precise. Okay. make this initial draw, and these are exactly the priors that I have. So this, I'm going to make 6 different panels, 1 per subject. I will first make an empty plot, and then for each subject, we'll generate 500 different regression lines. You will notice now I incorporate my random intercept, my subject-specific intercept right there. And I also now incorporate my subject-specific slope right there. All right. Let's see what we get. Uh-oh, I think I forgot to run something. I apologize for that. I forgot to run something because it looks like I got nothing. So I apologize. Let's try it again. All right. This is looking better already, better than an empty set of plots. So it usually takes it a little bit of time to render 3,000 different regression lines. We did 500 per subject, and we have 6 subjects. Very good. Okay. So now notice that I have a number of different regression lines. If you sort of blur your eyes, you can still definitely see that positive association. But there's definitely some regression lines that start high and actually go down. So what that would indicate is when you are on full sleep, you are slower than when you are sleep deprived for 8 days. So for example, there's a line right there where my cursor is, which is has a pretty downward slope. One line right there with a downward slope. There's a few lines there with a downward slope. And I'm also reporting, of course, the average subject intercepts. So this subject is about almost 3 milliseconds faster than the overall population mean. This one is 2.6 seconds slower. Now here we can start to sort of play around a little bit. And let me show you some ridiculous cases. So the presence of random slopes almost 100% of the time indicates the presence of random intercepts. Said another way, if my subjects have different slopes, that almost always induces different intercepts. Here, I will make it sort of obvious by pumping up the between slope standard deviation and pumping down the between intercept standard deviation. And here's what this looks like. And as this runs, think about what the slopes being super different, but the intercepts being very similar looks like. It's going to fan out in just a second. There it is. All right. So you should recognize this as being kind of a ridiculous set of prior simulations. If there is sort of a point at which all of these regression lines are forced to join, right? Because my between intercept standard deviation was set at 5. And then I'm forcing the effect of days to be super different between subjects. And so it's going to fan out. And notice I didn't touch these at all, right? Because I'm trying to develop an intuition for what these guys do. And so this sort of fanning out is why when we introduce random slopes, we 99.99999% of the time, as in I've never not done this, but I'm sure there is an application there somewhere. But the presence of different slopes almost always induces different intercepts. And that should make some type of intuitive sense. If we flip that, go back to our prior predictive simulation that I showed you last time, where I'm not going to allow for much deviation from the population slope now, based on this sigma here, based on this mean. I'm not going to allow a ton of deviation from the population slope. So this is going to produce lines that look virtually parallel. Even though they're going to be slightly different, they're going to look virtually parallel. All right, and it's just going to tease us a little bit by populating what looks to be one panel at a time. That's all right. You see, although not every line is parallel, as it would be if I really took the sigma down, they're a lot more parallel than in this case, where I forced the intercepts to be close together and fanned out the slopes. So neither one of those is particularly realistic. And here's what happens if we set the between slope standard deviation to be the same as the between intercept standard deviation on average. My take is this will also look unrealistic. We will be forcing those lines to fan out more than what is supported by the data. While this is running, let me flip back to my data set. So you will notice that there is just a tiny bit of a fanning out that's happening. Just a tiny bit. I'm sort of doing that. It's a little bit closer at day 0 than it is at day 10, but it's not quite the type of fanning out that I got originally. And this, what I have up on the screen, which assumes identical hyperstandard deviations for my sigma u's and my sigma w's, this is still fanning out way too much. Remember, this line right here is the maximum observed. And I'm on day, looks like by day 2, I'm off the observed data. You know, yes, we build priors for the world from which our data came from, not for our exact observed data set. Now look at this rogue guy. Look at this rogue little guy, where I'm allowing for a negative slope. And that's okay. Let's allow for a negative slope. It's 1 out of 500. Sure. I'll take that prior probability. But this is still too much of a fan out. So you often want to reduce the between slope standard deviation to be something smaller. And I went with 20. Okay. Flip back to R. Excuse me, not R. Flip back to the notes. That is how I arrived at these two values. Now, in the literature, you will see people go ahead and just set the prior to be identical for the two effects. But I think that's a little lazy, and I have to admit that I get lazy sometimes. If I'm, you know, a 5th author on a paper and they just need me to run a model, I might get a little bit lazy and set those priors to be the same. Figure out what they are for the intercept, and then say, well, if I that's probably too big for the slopes, but I'm being conservative here. You know, I'm being uninformative. You know, more prior uncertainty is less informative, so I'm okay with just being lazy. But I think that's missing an opportunity. That's missing an opportunity to fully use Bayesian analysis and fully use the power of the prior and use prior predictive simulation correctly. So you will notice that there's a lot of blue. The dark blue stays mostly within our observed data. There is some fanning out, but only a few lines, you know, go wildly above what we have observed or go wildly below what we have observed. With these hyper standard deviations, we seem to remain mostly within the data we have observed, and the shapes are much more similar to what our original observed data looks like. Okay, so do play around. The code is posted. Do play around with it to get a sense of how these parameters, what impact they have on our muse, right? What we have plotted was 500 of these 500 regression lines per subject for 6 subjects. So play around with these. Find a ridiculous case, right, where all the intercepts of 4 to almost joined together. Find the case where all the slopes are parallel by changing these hyperstandard deviations around, and then sort of develop an intuition for what this model does. So in R, it requires just a tiny bit of code to allow our random slopes and random intercepts to have different priors. And again, the extra coding, I think helps people be a little bit lazy, but that's okay. We really want to do a good job here. I want to teach you how to do it right. I'm not going to teach you how to be lazy. So here I have class SD, which indicates that I'm setting the prior for my between subject standard deviation. Here I say that it's an intercept, and my group is subject. I could have multiple levels of nesting. Remember, I can have subject within classroom, classroom within school, school within district, district within state, state within country. So in theory, you could set a different set of priors at every level of nesting. Here, we just have one level of nesting. We have days nested within subjects. And so that's why we have the code as I have it here. Okay. The rest of it looks very similar, something you guys should be very familiar with. You will notice how it's written up here in the actual formula. I'm having a problem with my stylus, which is, I'm just going to live with it because we're almost done with the semester, guys. See how that works? The intercept is included automatically. It looks like this: days, 2 vertical lines, subject. The random intercept is included in this automatically. You don't have to write 1 plus days subject. This is a more efficient way, and it includes the random intercept automatically. Okay, let's look at the output. As expected, the variability in the intercepts was about 4 times greater than the variability of the slopes. The 6.5 is the standard deviation of the slopes in reaction time per day. My population estimates remain very, very similar, almost identical. But my error term really diminished because as we explain more variability, as we allow each of our subjects to react differently to being sleep deprived, well, we explain more. We systematically account for more variability. We reduce the amount of uncertainty that is unaccounted for. And using that coef command, right? This is the coef of my model object, which is going to produce our subject-specific intercepts and subject-specific slopes. We have now different intercepts, as we did before in our first model. And importantly, we now also have different slopes. There are 2 subjects that must be fighter pilots or long-distance truckers, because number 309 and 335 are unaffected. All but those 2, so 16 out of 18 volunteers, their reaction time deteriorated. Their reaction time got slower as they were sleep deprived for longer. But we had 2 subjects, 309 and 335, who were unaffected. And so, if this was and this is a real study, I don't know if we're trying to understand what affects someone more or less. Of course, by the way, look how much variability in slope there is. Well, we quantified it, but we sort of have a group at around 10, 11, 17, double digits, but we also have this group in the single digits. So maybe we'd want to study what kind of genetic makeup we want to maybe take a cheek swab and study what kind of genetics they have, try and figure out who is more susceptible to lack of sleep, who is less susceptible to lack of sleep. These two subjects are extreme, but we did have some very non-trivial variability, like 310, 330, 331, 351. They were about half as susceptible as the population average, right? Population average was 10.5 milliseconds per day. The subjects I just cited were about half as susceptible as that. When we plot what that looks like, now we have, right, the lines aren't parallel. Every subject gets its own intercept and their own slope, right? The slopes are so different that the lines actually cross. And when we look at it by panel, we see that we're now fitting the subject better. That sigma error term now reduces because we now fit data from each individual subject even better. So if you look overall, our fit actually improved, and we expected this to be the case. And on the right, we actually have a new way of checking if we have successfully represented the relationship between some covariate and the outcome. And here my covariate is number of days. And you can see the raw data is the sort of the darker line, and the fitted data is the lighter line. And we see that the raw data is pretty well captured inside of our posterior samples pretty well. So I don't think that a quadratic, for example, is necessary here. In fact, looking at these panels, I'm not seeing a whole lot of curvilinear relationships. Now, if we took it out twice as long, if these are 10 days, if we made them do it for 20 days, would curvilinear relationships be necessary? Probably. But with these data, these precise data, not the case. I can always ask the question, how much did I gain predictively by allowing my slopes to vary by subject? So MRI is random intercept, our IRS is random intercept and random slope. And we can see that we have reduced that WAIC, and a formal comparison actually shows that we have about a 2 standard error improvement. In the WAIC. So WAIC improved, sigma error reduced. We saw a non-trivial amount of variability where I think something like 5 or 6 subjects were half as susceptible to lack of sleep. All in all, this is building a narrative that random slopes, subject-specific slopes, are absolutely positively necessary. Now, I want to show you guys something interesting about counting effective parameters. Here we have output from the random intercepts. On the right, we have random intercepts and slopes. So what we're really trying to estimate is 18 subject-specific intercepts, 1 population intercept, a days effect, and an error term, right? That's the sigma epsilon. So we're estimating 21 different parameters. But the software is reporting that we have 19 effective parameters. So by sharing information between subjects, we save having to estimate 2 parameters. With the slopes, the savings are greater. We now have 18 times 2 parameters. Why 18 times 2? 18 subject-specific intercepts and 18 subject-specific slopes. We still have a population intercept, we have a population slope, and an error term. So in this model, we're trying to estimate 39 different parameters, but the model is reporting 33 effective parameters. So we save 6 parameters by sharing information between subjects. There's more sharing that's happening. There's sharing in their starting point, the intercept, and there's also sharing in information about how they are affected by lack of sleep. So all of this is pointing to we need the model with random slopes. Okay, this next slide is as complex as we will get in this class. Now we have notes after this when we get into GLMs, the Bernoulli GLMs, but I promise that's actually not as complex as this next transition. Because if you remember for a Bernoulli GLM, if you understand how this mean is put together, just feed it into an inverse logit and go home. You're good. That's all. And now you have a multi-level Bernoulli. If you understand how that slope is put together and you have count data, just feed that, I'm sorry, not the slope, how that mean is put together. Just take the mean, exponentiate it, and feed it into a negative binomial or a Poisson or a zero inflated Poisson. Oh, wow, we're so complex. We have a multi-level zero inflated Poisson. So this next slide is sort of as complex as we're going to get in this class. And it's pretty complex on the scale of sort of intermediate statistics. Here's the big idea. We're still going to have a set of random intercepts and random slopes, but the intercepts and slopes themselves are going to be correlated. To be clear, this is not a correlation in the data. This is not the correlation in observed data. This is the correlation between the deviations from the population intercept and the deviations from the population slope. And the way we induce this is we draw these together at once from a multivariate normal distribution, as opposed to separately from a normal distribution. Right, you will notice that here we draw our intercepts, and then at a different time, maybe a millisecond later, we draw our random slopes. The most general way is to say, well, why don't we allow the random intercepts and random slopes to be correlated between one another, and let's draw them together as we do there. So why would we do this? I want to sort of, there we go. Here is the case where intercepts and slopes are positively correlated. So you're thinking, okay, they're positively correlated, which means when I start high, I increase faster. And when I start low, I increase slower. All right, positively correlated. If you start high, you go up and increase faster. If you start low, you decrease or decrease slower. If you start in the middle, maybe you don't change at all. This picture is when the correlation between intercepts and slopes is positive. All right, now you guys can imagine, what if I now want a negative? This is, by the way, very common in education, where students who have more sort of innate knowledge at, on day 0 might grow more. Students who have less, call it innate knowledge on day 0, may get confused, right? And not grow at all, or actually diminish in their educational outcome. This is also common in public health. States that have a high risk of opioid mortality to begin with, at the year 1990 or whatever, 1980, their they tend to increase faster. States that keep their risk low initially tend to decrease or stay flat. So positive correlation between intercepts and slopes is quite common. What would negative correlation look like? It doesn't happen very often because remember, this is systematic. This is systematic negative correlation between intercepts and slopes. Right, this is now negative. So here, you start high, you go down. You start low, you go up. Start high, you go down. You start low and you go up. Now, this is, of course, a pretty extreme case that I'm drawing for the sake of making a point, but there's not a lot of growth data that is like this. And of course, the case in between is when they're not correlated at all. Your starting point provides no systematic information about your growth, and your growth has no systematic overlap with your starting point. And that is the case of model 2 when they were uncorrelated. Okay, so in order to allow the intercepts and slopes to be correlated, we have to introduce this correlation matrix. And the entire correlation matrix, which in this case has just one parameter, right? It's this row parameter is the correlation between intercepts and slopes. But you can imagine that there are, okay, days and age, right? Why limit ourselves to only one slope? Here is another one, okay? And then this correlation matrix is going to be 3 by 3 if we introduce another covariate, if we introduce another slope. So don't be complacent. Although we have just one additional parameter, and this is new, we put a distribution on the entire correlation matrix. So far in this class, we've discussed distributions of scalars, of vectors even, but we have not yet discussed a distribution for an entire matrix. Now, the correlation matrix is interesting because it has fixed values of 1s on the diagonal. It can't be anything else. And the off-diagonal terms are, of course, symmetric. This distribution, LKJ distribution, is fairly new. LKJ stands for is 3 initials of the authors who first described it. I think it's Lewandowski, Korevichka, and Joe. And that's how they got LKJ. You will notice that I'm using slightly different sigmas, and I'm about to flip into R to show you how the prior predictive simulation works. Okay. First things first, let's go to the distribution zoo. And this is a very nifty little online app by Ben Lambert from the UK. So we go into multivariate distributions, and we go into the LKJ distribution. The smallest amount that it allows me to do is for a 4 by 4 correlation matrix. And what it plots is the correlation between dimensions 1 and 2, variables 1 and 2, and the correlations between variables 2 and 3. And this right here is corresponding to the LKJ1. This is going to be completely uninformative. In fact, we see that right here. The expectation of the correlation matrix, the expectation of my 4 by 4 correlation matrix is an identity matrix of equal dimension. So the average matrix is the identity matrix. And now we can see how the different samples, this is 2,000 samples of the correlation between variables 1 and 2 and correlation between variables 2 and 3. There's one more correlation that is not being plotted because this is a 4x4 correlation matrix. But you will see that we're sort of filling out the entire space. We're allowing for some very high correlations, and we're allowing for some very low correlations. We're allowing for this correlation parameter and this correlation parameter to be around 0. We're allowing for both of them to be around 1. We're allowing for one to be at 1, one to be at -1, or very close to 1 and -1. In fact, LKJ1 is completely uninformative. And that's not what I'm using here. But LKJ1 is used because it basically assigns equal prior probability to all correlation matrices of that dimension. We saw the mean was an identity matrix, and an LKJ1 assigns equal prior probability, in my case, to all 2x2 correlation matrices. That's kind of powerful. That's very uninformative. Here's what happens when I start to increase this, what Ben Lambert calls degrees of freedom. That's this term right here. Here's what happens. When I increase it to about 8. You see what happens? We start to consolidate the correlation terms. We start to consolidate these off-diagonal terms. I only have one. They have more than one because they have a 4x4. I have one because I have a 2x2. So what if you increase that number inside the LKJ distribution, you start to consolidate those correlation terms around 0. So you don't allow for extreme correlation as this term increases. And I wonder how much we will see that. There we go. In fact, we are now don't even allow those correlation terms to be more than an absolute value of 0.4. We got absolutely no samples such that the absolute value of the correlations was above 0.4, above 0.4. Go back to 1. We now certainly allow for correlations that are near 1 and -1. Let me go back and do my prior predictive simulation. All right, this is model 2 up here. This is model 3. This is the as complex as we will get in this class. I still draw my 2 sigmas. That happens independently. These sigmas get drawn independently. But now look, I make my 2 receptacles for the random intercepts and the random slopes. I still will make a set of 6. I'm going to do this for 6 subjects. I will still produce 500 different regression lines for 6 subjects as part of my prior predictive simulation. But notice, we're going to draw these together from a multivariate normal, mean 0 and some variance covariance matrix. The variance covariance matrix is describing the correlation between my random intercepts and my random slopes, not the correlation in my data. If that variance covariance matrix was describing the correlation in the data, it would need to be n by n. But it is only 2 by 2 because I have random intercept, random slope. If I had another variable here, like age, for example, maybe people who are younger can deal with lack of sleep easier than people who are older, or vice versa. Then I would have a third term here, and my sigma would then be 3 by 3. Okay. I have just 2 though. So I'm still going to make a draw of 6, right? I'm doing this for 6 subjects. My mean will be 0. And this right here, this line right here, is a random draw from a multivariate normal, MV norm, multivariate normal. I am performing this action right here where I have this, my arrow. And here my sigma is put together. I have a diagonal matrix with the ith sample of SDUs, sigma U's, and sigma W's. All right, there is my first sample. Here is my 10th sample. Here is my 100th sample. They're not the same, but you will notice that I'm inducing the variability of the intercepts to be larger than the variability for the slopes based on how I defined these terms. Right here is my correlation matrix. I'm using the RLKJ function that comes from this standalone R script. We're dealing with the outer edges of sort of what is taught in the statistics course. So there's not yet an easy way to produce random correlation matrices. So we have to kind of get a little bit creative here. So when I run this, it will give me a different 2x2 correlation matrix. And my eta is set at 3. So it's fully uninformative when eta is set at 1. But now, look, I'm getting a correlation matrix every time I run it. If you look at an off-diagonal term, that correlation parameter, it's staying mostly within less than 0.5, greater than negative 0.5. If I now allow this term to be 1, I should get more extreme values. And I just saw 0.76, there's 0.69, there's a negative 0.74, because now I'm assigning all possible 2x2 correlation matrices equal prior probability. Okay, so I will do this 500 times, and then I will simply reassign, I forget what my I is. Okay, this is going to be for the 100th sample. So here is the set of 6 random intercepts in the first column and the set of 6 random slopes in the second column. Why are the intercepts in the first column? Because that is what I put first into this sigma. And I put my sigma W as second. Sigma U's is first, sigma W's is second. Okay? So without further ado, the rest of the prior predictive simulation doesn't change. Here, I'm allowing the random intercepts to affect the, to modify my population intercept. Here, I'm allowing the random slopes to modify the population slope. The only thing that changed was we now generate random intercepts and random slopes together using a multivariate normal, and we put together the sigma using this LKJ distribution, where the LKJ distribution is the distribution of the entire correlation matrix. All right, from the top. So you will notice that I reduced the prior variability of both sigma U and sigma W. These are now 40 and 15, whereas before they were 50 and 20. Why? I'm introducing additional prior variability that is due to my correlation matrix, right? That correlation matrix bounces around these estimates. And so I felt like for me to get something similar to what I was reporting to you for the other model, I had to reduce those 2 terms. In fact, if I set them to what they were before, so that what I have right now on the right-hand side of my screen looks very reasonable. If I set these at what I had before, 50 and 20, I think there was a little bit too much prior uncertainty because now I introduce additional uncertainty due to the correlation matrix. Sometimes they come out as positively correlated, sometimes they come out as negatively correlated, sometimes they come out as uncorrelated, and I don't think that has yet updated. And now it has, and you can see there is that fanning out effect, that extra uncertainty that I didn't like. And this is going to be even more so if I set the between slope standard deviation to be equal to the between intercept standard deviation. So using the same priors as for my previous model, I felt that was too much. So I reduced it to 15 and to 40. With 15 and 40, I felt like I was not overstating the amount of variability in my data. And again, the extra variability comes from us introducing this random matrix, random correlation matrix. All right, so I think that right there has some fanning out. I'm now allowing for the intercepts and the slopes to share information by that correlation matrix. If I blur my eyes, the majority of the lines are positive, and the majority of the lines are staying between my minimum and maximum observed data. Although there's still a little bit more of that fanning out that's happening. So you could probably stand to reduce these by a tick, these guys by a tick more, maybe even 35 and 10, maybe 30 and 10. But this right here looks good. All right. In my code, I just have to add a prior for my class core, which is the correlation matrix. Here's the LKJ3. If I wanted to be completely uninformative, I could use LKJ1 and nobody would ask me any questions about it. I'm setting different priors for the between subject intercept and between subject slopes. Just remember, this is a half normal. This is a half normal because the class is SD for standard deviation, and I'm not touching anything else. All right. So the difference as well is in this term right here, where now I have just a single vertical line, which indicates they're correlated, as opposed to two vertical lines, which is that they're independent. The random intercepts and random slopes are independent. So I run that, and I get this. We have introduced one additional term. For these data, the correlation is very low. The credible interval comfortably crosses 0. So my random intercepts and random slopes are not correlated for these data. I allowed them to be so, whereas in my previous model, I assumed them to be so. So here, I can estimate this model first and then collapse down into model 2, as opposed to stopping my analysis at model 2 and not allowing the intercepts and slopes to be correlated. The rest of the parameters didn't change. We already did that. Here is positive. Here is negative. And I would like to sort of, here we are comparing WAICs. So RIRSC is the correlated version of the top model. And you will notice that my WAIC actually increases. So there is no reason to include a correlation between those random intercepts and random slopes. So I would go with model 2 for sure, not model 3. Okay. Most of the time, people allow for that correlation between random intercepts and random slopes, because otherwise you are assuming something that is untestable, right? If we allow for the correlation and it comes out to be 0, we can say we tested for it. Here's the credible interval. It nicely crosses 0. I will now go with an easier model and fit model 2 instead, as opposed to saying I stopped the model 2 because I don't like correlated intercepts and slopes, right? So always allow yourself to be more general and test for that correlation and then collapse down, or test for it using the WAIC as I've done here. Okay, guys, this is actually as complex as we're going to get. Next time, we will look at a Bernoulli example where every observation is going to be a binary outcome. And you know what? Even eyeballing this model, this shouldn't look that crazy. Hey, look, we have random intercepts, right? we allow each kicker to have its own intercept. What's the trick? This is on the logit scale, right? So it's a random intercept on the logit scale. We're going to transform it, feed it into Bernoulli, blah, blah, blah. I'm going to call it quits. We went through random slopes today that were uncorrelated, and then we allowed them to be correlated. And we showed that for the sleep data, this was not necessary, because when we estimated that correlation, it was basically 0. When we compared the models due to WAIC, the correlation was not necessary as well. But you should always test for it. Don't assume it's not there. All right, thank you guys for listening. I hope you have, I won't see you until after Thanksgiving. And so hope you guys have a safe Thanksgiving. Yeah, enjoy. Spend time with family safely and socially distanced. Thank you guys.